All right, let's jump right in. Today we're going to talk about a hidden force that controls, well, just about everything. From how you can smell coffee brewing in the kitchen to how engineers design massive chemical plants. It's called mass transfer.
You ever wonder about that? How things just seem to move on their own? A sugar cube dissolving, steam puffing out of a pipe. It kind of feels like magic, right? But you know what? It's not magic at all. It's one of the most basic rules of the universe just doing its thing.
So at its heart, mass transfer is just stuff moving from a place that's crowded to a place that's not. That's it! It's like nature just wants to even things out. And this one simple idea is one of the most powerful tools in all of science and engineering.
Okay, so things move, we get that. But the real question, the one engineers live and breathe, is how fast? And believe it or not, it all comes down to this one kind of magical number that controls the speed of everything.
All right, let's get our hands dirty with a real problem. Put on your engineer hat for a second. Your job is to figure out exactly how fast water is evaporating from this pipe into the air. We need to find the rate of transfer.
So piece number one of this puzzle is what we call the driving force. You can just think of it as the push. The more water there is on the pipe's surface compared to the air around it, the harder it wants to get out of there. It's just itching to escape the crowd. And then, well, there's the obvious part, right? A bigger pipe, it's going to lose water faster than a tiny one. So the surface area matters. The more doors you open, the more people can get out. Simple as that.
But here's the secret sauce, the thing that ties it all together. It's called the mass transfer coefficient, or Kc. This is our magic number. It takes all the complicated stuff, like how sticky the fluid is and how fast it's moving, and boils it all down to one single value for speed. So the million-dollar question is, where do we get this number?
Well, before we can find that number, we have to get to know our fluid a little better. We need to figure out its personality. Is it flowing nice and smooth, or is it just total chaos?
And the way we measure that is with something called the Reynolds number. Seriously, just think of it as a flow chaos meter. If the number is low, the flow is smooth, predictable. We call that laminar. But if the number is high, whoa, it's a mosh pit. That's turbulence.
And what's super interesting is how we measure that chaos depends on what we're looking at. For a gas, we look at things like its speed and how easily it flows, its kinematic viscosity. For a liquid, we're more interested in its density and how sticky it is, that's dynamic viscosity. But here's the thing, it doesn't matter if it's a gas or a liquid. The goal is always the same. Get that one number that tells us how chaotic things are.
Okay, so we've got our chaos number, we know how wild the flow is. Now we can finally go hunting for that magic mass transfer coefficient.
And this right here is the big leap. We've got this number for the flow, the Reynolds number. But how in the world does that tell us how fast individual molecules are actually jumping from one place to another?
The answer is another special number. It's called the Sherwood number. And its whole job is to be the bridge. It connects the big picture fluid motion, all that turbulence and swirling, with the tiny molecule-level action of things spreading out. It is the missing link.
So this all boils down to a super straightforward three-step recipe. Step 1, calculate the Reynolds number. Find the chaos. Step 2, use a known equation, basically a recipe that other smart people figured out to find the Sherwood number. And step 3, you just do a little algebra on the Sherwood formula to pull out our magic number, Kc. That's it. Okay, let's see it work. For that gas problem, we take our Reynolds number, plug it in, find the Sherwood number, and do the final step. And bam, there it is. The mass transfer coefficient is 0.00882 meters per second. That's our speed.
And check this out. We do the exact same thing for the liquid problem. Same 3 steps, Reynolds, Sherwood, solve. And we get the coefficient for the corroding aluminum. But look how much smaller that number is. It's because the situation is totally different, and our magic number knows it. It captures all of that complexity perfectly.
So okay, we can find the number. Big deal, right? Well, actually, it is a huge deal. This isn't just some math problem for a class. This is literally how we build our world. So, okay, let's dive into this. After all that math, you're probably thinking, what is the point of all this? Why do we care so much about this one little number? The answer is one word: design.
So here's the final boss level. An engineer is designing a chemical plant. They know exactly how much gas they need to absorb per second. They have a target rate. So the question changes. It's not how fast does it go, it's how big do I need to build this thing to get the job done.
And this is where the magic really happens. We take that exact same equation we started with, but we use it backwards. We don't solve for the rate. We already know the rate we want. We plug that in. And since we figured out our magic kk value, the only unknown left is the length of the pipe, L. We just solve for that.
So you plug in the numbers, your target, your magic coefficient, all the other properties, you run the calculation, and what pops out is a real, physical answer.
And that, right there, is the entire point of all of this. All that abstract theory, all those weird numbers without units, it all comes down to this one, solid, real-world instruction. Go build a pipe. Make it at least 0.724 meters long. That's how you turn math into reality.
So think about the journey we just took. We started just by wondering why coffee smells so good. From there, we learned how to measure the chaos of a flow, how to find the magic number for transfer speed, and then we used that number to actually design a real piece of equipment.
And this exact process, this way of thinking, it's everywhere. From creating artificial kidneys, to designing better ways to deliver medicine, to building systems that pull pollution out of the air. So the real question to leave you with is, now that we know how to find these numbers, what incredible things are we going to design next?